please.
Oh, okay, great. So, hi everyone. As you can see from the title of the slide, today we are going to dive deeper into the principles of operation of Bitcoin script. And Bitcoin script is a very important part of Bitcoin because it allows the users to transfer their coins and also not only to perform simple transfers from A to B, from me to you, but also to have more complex conditions that allow to implement additional level either of security or of some logic for spending the coins. First of all, let's look at what approaches there exist to set the conditions for distribution and spending of coins. The first one is Turing complete, and without getting too deep and too formal into what is Turing machine, what is Turing complete language, since I believe many of you already know this concept and pretty familiar with it. But speaking with simple words, we call some language Turing complete when it allows us to implement any logic we want, even if we are speaking about our own cryptographic algorithms, the ones that are not present in the system. You can implement them with the Turing complete programming language. And as you see from the slide, it is represented as the set of tools, very basic tools, and the very big manual which explains what can you do with these tools in order to achieve any goal you want. Several examples of Turing complete systems include, of course, Ethereum and all of its forks, layer 2 solutions, and other solutions that are somehow directly or indirectly connected with Ethereum and generally are running based on top of Ethereum virtual machine and the ones that implement Ethereum standards. And the Ethereum developers, creators even have created a programming language, which is called Solidity. And I believe many of you have heard about it. It's a very high level, very convenient programming language, which allows you to create almost any logic you can imagine and run it on chain. Also, systems with Turing complete language is Cardano, EOS, and Tendermint. The next category is non-Turing complete. These systems use building blocks to allow you to implement the logic only within the system boundaries. They are generally safer and more efficient, but at the expense of flexibility. Graphically, we can represent them as some blocks which are inside of the box. You can take them from out of the box and stack them together. But in order to get some meaningful result, of course, you need an instruction. And as you can see, it's way thinner compared to the manual in Turing complete languages. So it's in a way easier. It has less opportunities for you as the creator of the script to break the system or to implement some malicious code, but you pay for it with the flexibility. So you are not free to create whatever your heart desires. You cannot really make or implement your own unique custom cryptographic algorithm in Bitcoin, but well, you can work with whatever you have. And of course, the main example of non-Turing complete is Bitcoin script, which we will look in more details today. And the third category is templates. Templates represent a set of ready-made entities, like contracts or some other entities, which you as the person who wants to create conditions for distribution and spending of the coins do not need to create yourself. What you are doing is you are just filling the fields of the template. It's like when you go to the you want to get a passport, and they don't ask you to write everything from scratch, and God forbid they do not allow you to come up with your own structure of this official paper. They give you the pre-printed paper with blank spaces where you put your first name, last name, you put your identification information, you put the, I don't know, the date where you want to, when you want to get your passport or when you will be available, and so on and so on. The same works here. So you see, we have a template for transferring coins, we have the template for exchange coins, we have template for creating an account, and so on and so on. And what user needs to do is only to fill in the fields of this template. Of course, the most obvious, the biggest advantage of templates approach is smaller transactions and more effective. Generally, working with templates is more effective compared to non-Turing complete and Turing complete languages, because you are operating with something which is already pretty much standardized and optimized by the developers of the system who know their product best, and that's why it will be more efficient. But on the other hand, you are extremely limited in what you can do, and basically you hand the thinking process into the hands of system developers, because if there's something missing that you would like to have, or you would like to do some very fancy thing with the coin spending conditions, you will not be able to do that. Next, let's look at the features of Bitcoin script. So first of all, Bitcoin script is a stack-based language, and it uses a reverse Polish notation for its operands. First of all, stack-based language means that the operators and operands in Bitcoin are put in the stack. And the way stack works, just a brief reminder, or maybe for non-tech types, maybe it will be something new. So stack is a structure where whatever you put, you get from the top. So if you, and we will look at that more graphically on the next slides, but in a very simple terms, you always take whatever you put from the top. So you cannot take from the bottom, you cannot take from the middle. You only get it from sorry, I'm not sure what has happened, so I will make a few steps back and maybe repeat part of what you might have missed. Or maybe you could guide me when did the video stopped and the audio, when did they stop? You can write it in the chat, or maybe Olena or someone from the team can say it.
No, it's okay. It was 1 second.
Okay, perfect. Because I'm not always paying the attention to the green border and the Zoom interface, so I might get a bit carried away with the process. So yeah, the reverse Polish notation, we read it from left to right, and operators come before operands. So data first, numbers first, everything first, and the instructions go later. Also, in addition to our basic explanation of Turing incompleteness. Here's another more formal form, is that Turing incomplete means that the language has limited functionality and does not support jumps and loops. Jumps mean that whenever a compiler achieves the special jump command in the code, it skips all of the code in the rest of the program and moves, let's say, moves the cursor, moves the current execution cursor to the part of the memory which is specified in the jump. This is well, this concept is often used in low-level programming, like in assembly programming, for example. And loops, of course, it's the construction which allows to execute one fragment of the code, certain fragment of the code, several times, depending on the conditions. So reverse Polish notation, we have already got that. And yeah, this type of notation is much simpler than the usual algebraic one. Therefore, it entails fewer computational errors. And we will see it right now when we have the example, well, not really right now, but a little bit later. So by this moment, you may have asked yourself, what does script basically mean? So we are talking about this Bitcoin script, but what is the script itself? And the script is the concatenation of two values. The first value is script sig, and the second value is script pub key, and these values are concatenated and together they represent the script. The script sig can be thought as the lock-in script, so it is a conditions you put on an output to prevent others from spending it. It's like the lock you put on the output. And the script pub key is the unlocking script. It's the key which you use to unlock the lock on the coins. Every transaction has these two fields, and the script pub key, this unlocking script, usually, well, not usually, always actually, contains a description of some conditions that the user must meet in order to spend the coin. So you need to prove that you have the right to spend this coin. So either you are the intended recipient and you just need to prove that you own this address, or this may be some more complex conditions. And the script sig contains the data necessary to satisfy these conditions. And together, when we concatenate them, these fields represent the script. So here on the slide, we have a very
Is it problem only me or?
No. For me the same.
No, yeah.
Yep. So in algebraic notation, we have the operations in the brackets first. 2 + 4 goes first. Then we go simply from left to right. So it's we multiply the result by 5 and then divide it by 10. When we move to this stack-based notation, this Bitcoin script notation, so what happens is that we take the number 2, we put it in the stack, we take the number 4, we put it in the stack, and then comes the operator. So these numbers are called operands. They are the objects of operations. And the plus, the multiplication, the division sign, is the operator which performs some operation based on operands. So 2, 4, then we have the plus operator. Yeah, I see, guys, thank you for the comments, but it's not really the Wi-Fi problem, it's more the hardware problem, because my internet works well, and well, I just see it on my other device, which is like here above my head. So appreciate it, but it's not the Wi-Fi problem. So then we have the plus, which says that we add these two operands that are here. Then the result, we put 5, we keep this result in mind, add 5, multiply them, and so on and so on. It will be better seen in the graphical example. So here we have our operations, our operands and operators, and here we have the stack, and this is the order in which they are executed. So first we have 2, put it at the top of the stack. Then we have 4, again, put it at the top of the stack, above the 2, so not below, but above. This is how the stack works. Then we encounter the addition operator, which means add these 2 numbers at the top of the stack and put the result in the stack. So these 2 are destroyed and the result is put into the stack. Then 5, again, put it to the top, multiply these 2, destroy them, put result in the stack. Then put 10 at the top of the stack and do the division. We divide this by this, and we have 3 left in the stack. So once you have this graphical representation, I believe it becomes really, really simple. So what are the operations in Bitcoin script? What do we have in our hands in order to do whatever we want to do? So Bitcoin script has 7 execution control operations. They are enough to implement if-else logic and do a few other fancy things. And important thing here is that when we say that you can implement if-else logic in Bitcoin, it's not the same as jumps, because when we have if-else constructions, we only choose whether to execute the block of code or not. This is not the same as jumps in that we discussed previously. Then we have 19 stack interaction operations. For example, add to the stack, remove from the stack, swap values in the stack, reverse the stack, and etc., etc. Then we have 27 arithmetic operations, which, in addition to basic math like addition, division, multiplication, you also have operators like minimum value, maximum value in the stack, and etc. And 10 cryptographic operations, which include verifying signatures, hashing, checking the hashes, and so on. Let's look at them more closely. So execution control, just a few examples. OP if, so OP, they all begin with OP, which stands for operation. OP if, this is just simply if this, then execute whatever is stated. OP else, if not this, then execute the different branch of the logic. Not if is simply as the opposite of if, and if is more like it's not really, well, it is used to close the if else block. So this is the end of the if else block. And OP return is the operator which breaks out of the current code block and returns false. So this is usually used when something bad happens, or for example, if the signature is not valid, we do OP return, break out of the current script, and to the top, to whoever called the script, we pass false, meaning that no, this did not work well. Stack interaction examples: OP drop removes the top element of the stack. So whatever we have at the top, we just simply remove it. OP dump duplicates the top element of the stack. OP roll moves the nth element to the top of the stack. So it takes the element with position n and moves it to the top of the stack. Swap, OP swap, swaps two top elements in the stack. And OP rot, the third item in the stack is moved to the top. So it may seem like some of these operations are pretty specific and may not seem like the one you would use in a daily in your daily life or work. For example, OP rot, which why would you need to take the third item and put it to the top? But all of these operators were created with the specifics of Bitcoin in mind. So if they exist, it means that sooner or later, it is likely that you will encounter the need to use this operation. And it will be very interesting when we get to the cryptographic operations. But first, let's get arithmetic operations out of the way. So OP equal returns true and puts it in the stack if two top elements of the stack are equal. OP equal verify, it's the same, but in case when the condition is false, it breaks out of the code. So it does not put false in the stack, it breaks out of the code. OP add is addition. OP num equal is the same as OP equal, but for numbers. OP min and OP max find the minimum and the maximum value in the stack respectively. Now, as for the cryptography, so first we have OP ripe MD 160. This is the hash. This hashes the top element of the stack with ripe MD 160 algorithm. The reason why this specific algorithm exists in Bitcoin script is because Bitcoin uses this hashing algorithm to create addresses, to generate addresses. So when we have a public key and we want to ensure that it corresponds to an address, we execute OP ripemd 160, and if the values are the same, then this public key actually corresponds to an address which we were provided with. SHA-1 and SHA-256 are obvious. These are two hashing algorithms. Hash 160 is more interesting because it combines hash 256 and ripe MD 160. So what is going on is that it first hashes the value with SHA-256, and then it hashes the hash with ripe MD 160. And the reason why it exists, because this is the way how Bitcoin addresses are generated. They are generated by the double hashing, first with SHA, then with ripe MD. Hash 256 is the same, but with SHA-256. OP check sig verifies the signature. The difference here is that it checks only one signature and one public key. But when we are dealing with multi-signature, which involves several public keys, we have the OP check multi-sig operator, which allows to verify multi-signatures. What are the features of the stack in Bitcoin? So All operators except for pushing values onto the stack have no argument. So they operate only with whatever is at the moment in the stack. This means that these operations only work on values that are in the stack, and it's not possible to put a value that is not on the stack and input to the operation. So what it means is that you cannot, if you have no operations, operands in the stack, you cannot say add X and Y, which I input into this operator. You cannot have arguments for the operators. You can only imagine that you are also putting the operators in the stack, and they apply to whatever is below this operator. So you cannot do this imaginary math which is out of the stack. And considering all of that, we have to be mindful of the this stack is not endless, so there is a limit, and the maximum size of Bitcoin script is 520 bytes. This is done in order to protect the nodes from being overloaded with calculations, basically from draining their calculating power. And why we have 520 bytes is this is the maximum number of bytes necessary to specify coin spending conditions with multi-signature that has 15 public keys. This is the current limitation in Bitcoins, so you cannot have a multi-signature bigger than 15 public keys, but with the Taproot update, this number can potentially be endless, but so far this is what we have. Now let's look at the example of how Bitcoin script looks for P2PKH, and what it stands for, it means pay to public key hash. And public key hash is basically the address, or as we already know, a hash of a public key of the person who wants to receive coins from us. So we have the signature as an input, we have the public key, we have duplication operation, we have hashing with RIPEMD160 operation, we have the public key hash, again, it is the address, the hash of the public key, and we have OP equal verify and OP check signature. Now let's walk through this whole process and see how it works in the real example. So we move step by step from left to the right. First, the execution pointer, this is where the script looks at the current moment of execution. The pointer is at signature. And of course, this we only mark it as sig, but in reality, this would be an actual signature value, like hexadecimal signature value. So we see the signature here, put it in the stack, and move to the next step. The next is public key pointer here. Put this as well in the stack. Then we have duplication. So what happens? We take this public key and duplicate it. So now we have two public keys in the stack, and you will see why in the moment. Then we are doing the hashing with RIPEMD160, and this public key at the top turns into public key hash. And again, this is an address of the person which allegedly wants to receive the coins. Then we take the public key hash from the input and put it also to the top of the stack. So now we have two public key hashes, hopefully the ones that are equal, or at least they should be equal if for the person who is the recipient of the coins. Then we do equal verify, and this equal verified. So we have these two here. This two we don't touch, we touch only this two. And if everything is valid, they are simply just, well, dropped. If everything is valid, we just drop them. But if they are not valid, this will return false and break out of this script, and it will not proceed further. But let's say they are equal and we are left only with signature and public key. And if you look at the script here, you will actually see that they were specified at the very beginning. So when creating Bitcoin scripts, you need to be mindful of how the stack works, and you need to think a few steps ahead, and sort of like imagine the way stack will be processed once the script is executed, because these two values have been lying in the stack from the very beginning, and only at the latest step we finally check them with the check-sig operator. And check-sig operator basically it verifies the signature, this signature for this public key. And if the signature is valid, then we are left with only one value in the stack, and this value is Boolean, which equals true. Script is completed. If the result of the execution is true, it means that it can be unlocked with this script. So this script unlocks the inputs for which we want to apply them. Sorry, it unlocks the outputs. It unlocks the outputs for which we want to turn into our inputs and get them for ourselves. There is an interesting type of transactions of Bitcoin scripts, which are called transaction puzzles. So one of the probably most prominent, the most not maybe the most interesting, but the most well-known and prominent is the transaction puzzle, which was created in 2013. And in order to receive funds from this transaction puzzle, one had to provide two different lines of text that would produce the same hash with the SHA-1 algorithm. Basically, speaking in a very simple words, being very concise, in order to unlock these coins, you had to find collision in SHA-1 algorithm. So someone had doubts that SHA-1 algorithm is not is prone to collisions, and basically all of them are, but it's the question of how probable you are to find the collision. But someone wanted to prove that SHA-1 is already too vulnerable, and it needs to be we need to move on to something stronger. So they have created this transaction puzzle. And interestingly, the collision was discovered only in 2017. And only in 2017, when the person provided these two different lines of text, both of which with the same hash value, the same resulting hash value, this person has unlocked this this puzzle and transferred the coins to their address. So pretty interesting, and there are different puzzles, and even the ones you can create yourself if you want to do so. So this is it for the main material of this lecture, and now let's move to the questions. I see a red number on the chat, but I see that we had a couple of questions and they are all answered. So if you have any more questions now, it's a great opportunity to ask them. Yep, I see question from Anton.
Hi, Alexei. Thank you very much. I just wanted to ask a question on the order of operations in the script. So you've had these few slides with the with an arrow pointing at the exact operation that you were discussing, and there were two public key values which were hashed one after another. Could you talk through a little bit more about that particular process? How was the one hashed at the beginning, and then something else was applied to the other public key? I don't remember what it was, but basically somehow you turned both public keys into hashed keys. So how does that process happen? What's the order of operations there? I didn't catch it.
Okay, I see. No problem. We can walk through this one more time. So
this one is clear, at least to me.
Yeah. But keep in mind that these values in the these things are the input values that we explicitly put inside of the stack. They are not the result of operations. They are the inputs we put in the stack. So we put two public keys, right? A duplicated public key. So we have two of them.
Yeah.
And then we apply the hashing, and the hashing applies to the top element. So this public key at the top turns into public key hash.
Yeah, that makes sense.
The next thing we have is an input. It is the alleged public key hash that someone provided, someone who wants you unlock the coins. This is not the result of operations. Right. This is input. Like it's his address that he says, I want to unlock the coins with this address. This is the signature, this is my public key, and this is the address that I am providing. So we are checking whether this public key corresponds to the provided, explicitly provided address. I'm glad that it makes sense now.
Thank you. Yeah, because I thought both public keys were hashed, and I was confused. What's the order of operations there? But now I understand. Thank you.
Great. Yep. Recommendations. Yeah, I agree. It's best to look at the Bitcoin wiki, and we still have time. But do we still have questions? Do we or don't we? Okay, I believe then if we don't have any more questions, we can wrap this up.
Okay, thank you very much. Thank you for a lot, Alexei. Thank you for our students, and please wait for our new task for you. And see you soon. And
thank you.
Maybe.
Thank you very much.
Bye-bye, everyone.
Bye-bye.
See you.
Bye-bye.